welcome to this webinar where we'll look at the RTI Scatter Probe in a little bit more detail. But we'll give this a couple of more minutes. I see we still have attendees joining. So we'll just give it a couple of more minutes before we start the presentation as such. For your information, this is the first time that we're using this platform for a webinar, so please excuse any glitches that we may have along the line, but I think we'll run smoothly. We had a dress rehearsal a couple of days ago that worked pretty well. And also this time I'd like to thank Bergen Healthcare very much, and in particular Mr. Rakesh Chaudhry for organizing the webinar for us. It's been a good run. We've had a record number of sign-ups for the webinar, for any webinar that we've hosted, to be honest, and we're very pleased with that and very thankful for the work that Mr. Chaudhry has put in to get this done. At the end of the webinar, I hope that we'll have answered many of your questions, if not all. And if there are still any remaining questions that pop up afterwards also, there will be a reminder email, and please get in touch with Bergen Healthcare, and we will work together with Bergen Healthcare to answer any of your questions on this topic. In the platform here, there is an opportunity to raise your hand to react, and if you have a question, please do so. There are also a chat where you can post your questions, and we'll try to answer them as efficiently as we can when we move along. That is about it. I think all your microphones are switched off, are in mute. And also all of your cameras are automatically disabled for the sake of bandwidth, to maintain a good bandwidth for all of us along the line. Yeah, but if there are any questions, please don't hesitate to post them on the chat. And if there are anyone further afterwards, of course, then we'll take care of them as we move along. All right, I think we'll now 3 minutes past the hour, so I think we'll make a gentle start on it. In this presentation, then we'll look at briefly just RTI. What is RTI? Well, we've been around for quite a while. We're now 45 years in this business. It started off as a thesis project at the Technical University in 1979, the first studies of a non-invasive KVP meter, and the first prototypes saw the light of day in 1979. And this is what it will look like. That was the very first prototype. The first commercial non-invasive KVP meter was launched in 1981, and since then we've been launching new products and new innovations onto the market with quite a steady pace, I would say. We're the first then to have a multi-probe approach with the Barracuda 25 years ago. 20 years ago, we saw the red piranha that was then updated to the black piranha in 2014, which has now been a workhorse for many of the large operators and manufacturers in the world. Parallel with that, we've then, of course, had our Ocean software, which is the world's only QA software dedicated for X-ray QA and testing. 21, that's 5 years ago, we launched the RTI Scatter Probe. That was in the tail end of the COVID pandemic. So that was quite an interesting launch. It's a new technology, and it has taken some time for it to get a traction in the market. We're now seeing quite a pickup in the interest of the scatter probe. I hope that will, after this webinar, we'll see a similar development also in the Indian market. Then 2 years ago, we launched the RTI Mako, which is the latest software that we have in, or the latest instrument launched into the field and into the market. It was a long time since we had a new release of a high performance system into the market in the world. Now with the Mako system, we have a very, very good platform. You may wonder, why do we call it Piranha? Well, it traces back to the time with the Barracuda, when we thought we'd have an aggressive name for a very powerful tool. But after that, of course, we had the Piranha, which is also quite a powerful fish. And so that was it. We then have for the, oops, sorry, wrong way, wrong direction. There we go. Cobia is another instrument, not as fierce, not as strong as the other one, but quite a good fish anyway. And the latest one, we have the Mako, of course, which is the fiercest and fastest shark in the ocean. So that's why we thought we'd launch that, use that name. The fastest and the most powerful fish in the seas. I need to learn how to use these keys. All right, so this is RTI, global presence. We have our sorry. There we go. I wanted to use the laser pointer. There we go. So this is Sweden, in the top of Europe, west coast of Sweden. That's where we have our headquarters. We've got a sales office in the UK, one in Singapore, and then we've got a sales office and calibration laboratory in the US on the east coast of the United States. We work together with all the large global manufacturers, and we have close cooperation with many of them. Most recently, we have worked with Hologic to include the scatter probe as part of their standard kit for their field service engineers. So that's when we're talking about the scatter probe. Previously, they've had they're using the Piranha for the KV and dose measurements and HVL. And with the scatter probe, they're then checking the leakage of their DEXA machines and also their machines going off the manufacturing line at the end of line testing. But of course, with GE, we've got worked together with Canon, Shimadzu, Agfa, Sedical for the generators, etc. So we have close cooperation with many of these larger manufacturers. Just to orient ourselves also, we are in the field of medical X-ray. So X-ray, of course, has a large application area. We have the industrial with pharma, with luggage scanning, oil and gas, etc. Some applications are applicable, but that is not our focus area. Therapy also uses X-ray, but on the larger side of it, with the mega electron volt for the therapy side, we are not operational. We don't focus. We are focusing on the KV range of applications, which is on the therapy side, on the onboard imaging or the planning stage simulators. That is a KV area, typically a CT or a CBCT. That's the only part of the therapy application that we are active. But the main focus area is on the diagnostic X-ray imaging and the medical field. So mammo, surgery, vascular, rad, fluoro, vet, CT, dental, DEXA also, although it's not an imaging technology, but we do work with DEXA, the bone densitometry machines as well. To cater to all these, we've got a family of products, Piranha, which many of you may know. It's a family of a range instruments. We've got the cobia that we talked about earlier, which is then more docile, and scatter probe. To have all these work together with the Mako family, which is the latest one, of course. We have then also a larger range of probes and detectors to cater to and to handle all of different application areas. For instance, DAP chambers, which is dose area product, which is suitable for dental CBCT, for instance. CT ion chambers of very high performance, CT dose profiler for measuring the CT beam width, etc. And all of these then can be combined into serving a large area of the usage in the X-ray diagnostic imaging field. And to help us with all that and to assemble all of the data, we have powerful software, which is the Ocean Next software, which is then a powerful tool to help compile and analyze and evaluate the data that we collect from the field, which is then applicable to all the products that we market. So it's the same interface regardless of the tool and the instrument that you're using. Now, moving into the topic for today, which is the RTI Scatter Probe, which is one of our instruments. It is a leakage and a scatter detector in one. So although we call it the scatter probe, it is then suitable for leakage measurements, scatter, and also room survey. It is a solid state. We're using solid state instead of ion chamber based ones for a number of reasons. We'll come back to that. But when in that design, we work together with some of the manufacturers also to figure out what do they actually need. Well, many of them were looking for something which is robust, which is independent of air temperature and air pressure, which is easy to transport, and which has the stipulated and the right size according to the regulation. Although you can argue that, well, it measures in the same way, it doesn't do anything, but regulation is regulation, and if you want to follow it, well, then with the scatter probe you can follow the regulation because it has the regulation size, 100 square centimeters and 10 square centimeters, those two active areas that are operational. So then there's no fuss. It matches those regulations. And those regulations are in the CFR code, which is we call them FDA for the American market. That's chapter 21, and this is then the section 1020.32 and 30. And then the IEC standard, which is the international standard, of course, and we've got two standards here, and for both of them, the size and the performance matches. And they all say all these standards call for an active area of 100 square centimeters or 10 square centimeters, depending on what measurement you want to perform. The benefit here is that there's an automatic energy compensation in the scatter probe. That means that we don't need to worry about what is the mean energy, because that is worked out by the scatter probe itself. It has a wide range of operation. The operational range is from 10 keV basically up until 150 keV, which it covers the mean energies in the typical spectra that we have in the diagnostic imaging field. So that makes it then suitable for manufacturers and medical physicists across the world to use it. And with the solid state technology, it has a fast response and high sensitivity. So well, it makes it an interesting tool to work with. But being an interesting tool, of course, we need to understand how it works, and this is the objective of this webinar. Again, for the scatter probe on the front, you'll see that we had 100 square centimeter active area. That's a large area, and we can, which is used typically for leakage testing, and also for room survey and for measurements of scatter, etc. That's a typical one, 100 square centimeter area, and it's 10 by 10. It could be anything down to 5 by 20 centimeters. According to the regulation, but we decided let's make it square. It's easy and it's fair, so we're using it at 10 by 10 centimeters. That's 100 square centimeters. There's a smaller area also, which is 10 by 10. Sorry, 10 square centimeters, which is used typically for barrier testing. So for some applications, when we're looking at that's called for the barrier testing, the 10 square centimeter area. Those active areas consist of a matrix of solid-state diodes, where we use the same technology and the same principles as the high-performance meters, Mako or Piranha or Cobia, where you have diodes in the active area with known filtration, different filtration, but they're known and calibrated to that area. And if we have several of them, we can then work out not only the dose, energy dependent dose reading, we can also work backwards through the total filtration and HVL tables and figure out what is the KV, the energy that we're looking at. So knowing the energy or estimating the energy of the spectrum that we're looking at, we can then adjust or compensate for the energy dependence, because we know what the energy dependence is over within the spectrum, within the KV range for different KV readings. So so then we have oh, sorry, the voice, somebody said the voice is not clear. Maybe the speaker is, I need to speak a bit louder. I'll try my best. I have the concentration here, the compensation, and it should be automatic. Anyway, I'll try my best to speak up. Anyway, so we have that the active area. So we can estimate the mean energy of the spectrum that we're reading, and we can thus compensate automatically for the energy dependence and give a compensated dose reading or a compensated ambient dose equivalent reading as well, all the way through the full spectrum. And that is something new, something which we need to understand how that works. All right, and then we've got to get a decent reading also, we've got a built-in algorithms there and the electronics that are on board. They are quite recent. They're modern processors that can actually then work with lots of signals coming in from the diodes, where they work with ratios. And since we have filtration between the diodes, that will give us a ratio of radiation, and working and combining these different ratios with known where the filtration is known, we can then work out what the level is. And also being modern, they're quick, they're fast, so they have a very fast signal response as well on top of everything. So that's pretty nice. This means that we can then work and have a well-defined trigger threshold, which is 5 microgray per hour, which is quite low. So it is a very sensitive instrument, even with automatic trig. So it's 5 microgray per hour, or 0.6 MR. Or if you're looking at the ambient dose equivalent, that's 10 microsievert per hour, which is the threshold for automatic trig. So that's looking at the rear of the scatter probe. We've got then a start button for if you want to manual trig, you set it to, we'll look at that later in a while. We'll set it to a free run mode. That's what we call the manual trig. Free run is you start it and you let it run free until you stop it. That's the free run mode. So then you have a button on the rear, which is then for start and for capture of the data. There's an LED array that then indicates the radiation level at the back as well. And there is a possibility to set limits. So then you will have a red LED lighting up here when you reach the LED will turn red when you reach the limit that you set, that you define as the maximum for the radiation. And there's just to make you familiar, and we've added a little bit of a ticking like a Geiger-Müller tube, a GM meter, where you have that ticking sound, where you have the avalanche launching of the radiation and avalanche launching in the GM tube. So it's just an audio feedback that now the measurement is starting. It doesn't increase with radiation. It just lets you know that, okay, we've now started a measurement. So you hear it tick, 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 until the reading is done, measurement is done, then the ticking will stop. So that's just an audio feedback for it. Then we'll see, okay, thanks Petra. So then when we're taking it into the field and start measuring with it, of course, we need to use there's no display on the scatter probe as you saw. So we have to connect it to a Windows platform, and that could be a laptop or a tablet where we can run the Ocean Next software. And the Ocean Next software is connectable. You can connect it to the Piranha, to the Covia, to the Mako software, and now also, as you see, to the Scatter Probe. Scatter Probe requires the Ocean Next software for compatibility reasons. So when you connect the Scatter Probe, it will automatically identify, and when you start a quick check, this is the first screen that you will see. So you have then the choice of different modes of operation. You can either measure the air karma in gray, milligray, microgray, or MR, or micro R, whatever. So when you're looking at leakage measurements, this is the mode that you'd be using. If you want to do a room survey, for instance, to check the radiation risk levels, then you'd be looking at the ambient dose equivalent, and the measurement unit is Sievert. Microsievert, millisievert, or whatever you reach, this is the one that you'd be choosing. And then maybe for research or just for your own study, you can have one which measures and displays the mean energy of the spectrum. So we'll look at these different displays just now. This is what you'll see. So the screen that pops up has displays in it, which gives you the momentary dose rate, the air karma rate. It will give you the peak karma rate. It will give you a time also, which is then more or less the measurement time that the scatter probe is performing the measurement, and the accumulated dose, the accumulated air karma during that measurement session that we had in place, or measurement event that we had in place. So those are the things here. The trick here that we see is that we've got the curve, the dose rate. When if the measurement goes beyond 2 seconds, that window is going to show the karma rate over the last 2 seconds that we're seeing, the momentary. So that will start fluctuating back and forth. And when you then finish, it will make, according to the definition of a dose rate value, it will take the accumulated dose and then divide it by the measurement time or the event of the radiation. There is then one here, which is the peak air karma rate. Now we need to understand, and we'll come back to that in a little while to see what's going on. And that's tempting to see that, yeah, well, in the regulation, we see that we have the maximum of a certain dose rate maximum, or a certain sievert per hour maximum that we need to stay below. The challenge here that we see is that, well, there are burst events that we experience when we make a longer exposure time that can influence this. And if you have a fast instrument like the scatter probe, it might pick up reading, it might detect even these small bursts that could be milli or microseconds even long. It might be able to pick that up and detect it and display it. So we need to figure out what are we looking for? What kind of event, what kind of measurement values are we looking for in this area? So, but we'll come back to that. So just to keep that in mind. Similar thing for the ambient dose equivalent. We've got the rate value here, the peak, and we've got the accumulated value at the bottom. Now we said the mean energy. This is then the mean energy mode. We'll get a value here, which is the KEV. Important to remember that is not the acceleration voltage. That's not the set value we have on a machine. It is the mean energy of the spectrum. So is the HVL. That's the HVL, half value layer of the spectrum, not of the filtered output from the tube. So those cannot be compared to what we see on the console of the machine, if it's a CT scanner or a radiography machine. So this is then the spectrum. And what do we mean by the spectrum? Well, this is the spectrum. So we're looking at the mean energy of the spectrum, and the mean energy is down here. This is the mean energy, not the acceleration voltage, which is up here. So we need to keep that in mind. Same thing as for the HVL. It's the HVL value for the spectrum, the complete spectrum, not just so that's the mean energy mode, so we know what we're talking about. But this is the way that we understand, and we can compensate internally inside the scatter probe to figure out what is the mean energy of the spectrum and how do we need to compensate for that, the values that we have, so that we arrive at an accurate air karma or an ambient dose equivalent value internally. That's how we use it. So this is just a proof of the pudding. Proof is in the pudding, and this is the proof in the pudding here, that we actually do that properly. Here are some examples of what it might look like when we're having a measurement. Now this is a pretty solid. It's a 28 nanogray reading. What we've got here, the peak rate is 23, something like that. The air karma rate average, of course, is in 206 somewhere, and the peak is up here. So that's pretty easy to read. If we go a little bit lower, then we'll see that with 4, we'll still see a pretty good reading here. And here is one which is even stronger, 69 microgray per hour, and it's picking out pretty well in here. We'll talk a little about response rate, but already now we can see that here the response is from 500 milliseconds. That's when the radiation starts until it reaches the maximum. It's from 500 to 1,000 milliseconds. That's half a second response time. So just as a mark, just keep that in mind when we move forward. If the radiation is lower than the trigger level, we can turn on free run mode, and this is free run mode. So this is the toggle button right down here. If you click here in the software, you will then switch between free run and normal mode, which is the automatic trigger. Here we go. So this is then set for free run mode, and that can be seen by the information we have here in the yellow box up there. So it's in free run mode, and it gives us instructions. Click on the start or the button on the scatter probe to start the measurement. And here is the start button. And you saw from before, on the rear, you have the thumb button on the rear to start the measurement. That means that you can then start the measurement, make your exposure, and then stop and capture. And this is what's been done here. And then we can see that, yep, it's detecting, it's starting here, it's detecting nothing. And here, all of a sudden, we've got a measurement that starts and detects a measurement. Quite low, and it's 29 microgray per hour, so it's not terribly strong radiation either, but we're getting something here. And then again, look at the response rate. From here, that's 400 and something, 4,000 milliseconds, and it's up here. So it's less than 1 second until it reaches the maximum of it. So it's less than 1 second response time. Again, just to keep that in mind a bit. Here again, something which is a little bit stronger, 11 peak dose rates values are pretty okay. It gives us a strong response and a fast response. Lower dose rates, yeah, just repeating some of them, that just out of interest. And what do we have here? Again, it's with the ambient dose equivalent. Gives us some values here, quite a low value. But again, looking at the response time, we see that it's in the order of magnitude of half a second or similar. But that gives you then an understanding of what's going on. Another peculiarity, but something that may be of interest also, or for you to understand, is if we do then, like I did here, I did just free run with nothing in there to see what's going on. I did it and had a measurement for 3 minutes, and this is what we saw for the first time. There's just more or less random measurements, not very strong levels of radiation. There is no accumulated air karma because there is no radiation. I was doing it in my office, so there was no radiation there. There's no average air karma rate, but we do see a peak karma rate. So it's picking up something, a burst of something, could be a pion or whatever, photon arriving from space maybe to disrupt it. But there is something, but that is so little that it does not even impact nanogray to the 10th decimal. So if I have 10 decimals of in the nanogray region, it does not register. It does not accumulate even that much. That means that so if that is the case, then we need to figure out what impact could it have if it's not even noted in that level. But there is a small spike. We'll come back to it in a while. But I just wanted to illustrate this to let you know what's going on. And to how to evaluate the different displays that we have, because we need to understand what are we doing, what are we looking at, what are we seeing when we're doing these measurements here. All right, so we'll come back also towards the end a little bit about the software, because it does have the possibility to let us work with the software in a structured way when we're in there. Now, so looking at the leakage, what we're applying it and using it for leakage is then from the tube, if it's an overhead tube, or if it's an underhead tube, it's the emission of radiation, unwanted radiation from the tube itself. That's the leakage. The scatter on the other side is how the radiation splashes out from an object. But typically, it would be the patient, because that's the largest object we have in an X-ray room during that examination. So that's the X-ray hits the patient, and it splashes away in all different directions. And that is the unwanted radiation that might escape the X-ray room, the examining room, and which we want to block with lead lining and doors and lead windows and stuff like that, lead glass. So that's why we want to look at leakage. For the tube leakage, of course, it will then spread from the tube in all directions. So we need to monitor that. So to understand how much is that, there are limits for that in the room, of course. But we need to understand how much is it, and what contribution it does to the radiation risk outside the examination room. So those are the different levels that we have. It's 100 mR or 0.88 milligray for the FDA regulations, and in the IEC they rounded 0.88 up to 1 milligray in 1 hour. So, and here then for other areas here, it's when it comes to barrier testing, this is then what we're using them to check barriers. The key word here is in 1 hour, not per hour, it's in 1 hour. That's very significant when we're looking at the peak dose rate data that we're getting from some of the machines. But here it is in 1 hour, and that means that we need to adjust for the workload to see how much radiation escapes the tube during 1 hour. So in 1 hour, not per hour, in 1 hour. So what we need to do then is to make a measurement, an exposure. We measure it and then look in the documentation to see how many exposures like this can be performed during 1 hour, in 1 hour, and then multiply these exposures by that value to see is that below the legal limit or not. So that's what we need to do. It is tempting to look at the peak values on an instrument, but then you need really to understand what you're doing if you're using that as a value to pass or fail an installation, because it could have some impacts on it. We'll come back to that in a little while. Looking at scatter, well, that's then what escapes from the patient, so splashes away from the examination room. And the stray radiation, unwanted radiation, is then what escapes from the patient, what is splashed from the patient, and what is leaking from the tube. And how does that affect the different adjacent rooms around here? That's where we're looking at. The lead glass, the wall into a corridor, the wall into the ambient air, door jams that we're looking at for the rooms. How much does it escape there? Those are typical points of interest when we're looking at the room survey. And they've got, of course, different limits for that. For ICRP, for instance, IAEA have their recommendations. And one typical one is, okay, for staff, it's then 20 millisievert per year. And that's averaged over 5 years. So 1 year you may have 50 millisievert, but then it needs to drop so that you, over 5 years, have an average of only 20 per year. And then the public, like us, who are not working there, that's 1 millisievert per year, averaged over 5 years. So those are the ones that we have. Just to give you an idea, 5 to 10 microsievert is dental x-rays. And then the annual dose for a flight attendant, of course, they get a radiation when they're flying. It's 1.5 to 1.7 millisievert. And then when you're eating a banana, somebody found that the potassium in a banana has an isotope that emits radiation. So the banana equivalent is 0.1 microsievert. So you'll have to eat quite a lot of banana to come into the risk zone, but there's just to give you a comparison there. So this is what we're then looking at, the risk evaluation. That's when the sievert value comes in. The air karma is an absolute value. It's the absorbed dose. When we come to the sievert value, then that is an estimation of risk. And when we're looking at ambient dose equivalent, which is a typical value that was used for X-ray in this application, it is called H star 10. It's the estimation of what a dose would be to a point 10 millimeter under the surface of the reference sphere. So that would be then 10 millimeters into the skin, basically. That's how to estimate the dose. So then there's a formula for it, looking at the air karma, looking at the energy levels that then we have in there, because then higher energy penetrates more into that sphere, into those 10 millimeters. So these different factors, you put them into a formula and you arrive at the ambient dose equivalent called H star 10. 10 is then the 10 millimeter. There's one for the H star 0.07, which is for eyes, the ambient dose equivalent, the risk evaluation for eye radiation to the eye, for instance. So they're different ones. Typical ones for a room survey would be the H star 10. And that's the one that we're using for the sievert in values in RTI Scatter Probe. So then this is then again looking at the schematic fallout. You measure the reading. There's the occupancy factor. You take the reading and you factor in how much, how often are people in the changing room, in the office, in the corridor. What is the risk involved here? So that needs to be factored in also if you want to do it in a smart way. And here are some typical areas of interest: the lead glass, the door jams, etc. To see, because they could change over time. Especially door jams could be a little bit changed. When we then look at leakage and scatter, well, end-of-line testing for tubes. X-ray machines, before they leave the manufacturing site, they're typically tested for leakage, installation and acceptance testing, and also inspection of X-ray, or when you change an X-ray tube, for instance, that may be an occasion to check for leakage as well. Airport scanners, typically also, and then when you make larger changes to the machine itself. Then measuring leakage, well, it's done with the collimator closed, and you put it to max kV or max mass or whatever else setting you have recommended in the machine manual, and you measure in 5 directions: the top, and then anode, cathode, front, and rear. That's what we need to measure. Under the collimator, you never check because that's assumed to be pretty tight. Put it at 1 meter from the focal spot, and you make an exposure, and you make your reading, and then compute the values to see what you have, and what that would add up to during 1 hour of operation. If you have a tube like this, instead of trying to jig it, jerry rig it up above, you might be able to swivel the tube and make the measurement from the top just by rotating the tube. Scatter measurements, typically what you would be doing is have a scattering object in the beam. One good example is 20 centimeters PMMA. Could also be a water phantom and a bucket of water, but for reproducibility's sake, it's a 20-meter stack of 20 centimeter PMMA. Fully open collimator, and then the typical set values that are recommended, and then you measure the probe in where you want it to be, depending on what value you want to do. Maybe it's for the lead glass, maybe it is the door jam, Maybe you want to do a study of the radiation profile, of dose mapping of what's going on, and for research purposes, to see what kind of radiation levels do we have when it looks maybe like this for a research paper or whatever. So that's what we were looking at. Now, we have then some comparisons when we launched it here, and we've of course got a lot of feedback that comparison against a traditional survey meter, it may not match. It's looking at something and it's, well, we're getting a different value, different reading. Well, there is some fundamental differences. The scatter probe is a solid state meter. The survey meter typically is an ion chamber based system. One of the big differences here is the response time. If you're looking at a traditional survey meter that we're looking at it, we have response times from 1.8 seconds, 2 seconds, something like that, up to 5. We've even seen up to 8 seconds for very low level radiation, very weak radiation, where it needs a longer time for it to adapt. We have other solid state survey meters that have up to 2 or from 2 up to 8 or 10 second response time, which may be okay if you're looking for a geographical survey. If you're looking at isotopes in your department, your nuke med department, or if somebody lost uranium or some other radioactive waste, that may be, which is then just continuously emitting radiation. That's fine, then you'll be able to use that. But for shorter events like in the medical X-ray, then maybe 1.8 second even may not be fast enough, or you need to factor that in at least. With the RTI Scatter Probe, as you saw in the examples that we have there, the response time is always less than 1 second, often significantly less than 1 second, which is then more practical and more realistic from the point of view of medical X-ray, where you may have shorter exposure times, shorter radiation events. Now, what does that mean then when we're looking at the response time? What impact would that have? Well, I've tried to illustrate it a little bit here, but by saying that, okay, let's say that we have an event that happens, a very sharp rise in radiation levels, start of an exposure, for instance. Then the meter will then respond. It will give you a readout, but it will take time for it to adapt. And this is what I try to illustrate then, the readout from a meter, whatever it is, with the yellow dotted or dashed line here. The definition of the response time is when that reading reaches 95% of maximum. Sometimes it's 90, but 95% of that. That is the response time. That's the definition of the response time. Right, so now we have that settled. For the response time is for the time it takes for the meter to reach a readout that matches 95% of the actual radiation level. Now, what happens if we have a shorter event, an exposure time which is shorter than the response time? Well, you'll see here that it comes up only to this level, and then it doesn't go up any further because there's no radiation, so it drops here. That means that we'll have a gap here, where that the reading of the dose rate value in this case, of course, would be lower than the actual value. So this is then an impact that we may have and that we need to factor in when we're looking at the readings that we get from different types, when you're comparing two different technologies with each other. That may be this may be a contributing factor here that we have. And here I'll try to illustrate again here what that could look like in practice. if we have a level radiation that fluctuates like this, for some reason, I don't know why, and we have a small spike here, something that just happens here. If you have a slow system, it may not pick that up because it's too quick. It'll just make a small bump. It won't be able to read the whole bump, the whole stick here, the whole short event right here, because the response time of that system may be too long. So it may not be quick enough. And so this is a little bit of, it might be one of the explanations that we're picking up, and we're seeing dose rate or peak dose rate values, because the scatter probe picks up this short event right here, and but it's insignificant really in comparison to others, and where other probes may not see that in the event. All right, I need to skip forward a little bit here and move into another factor, which is a difference between the scatter probe and ion chamber based traditional ones, and also some other solid state survey probes. It's the impact from energy dependence. And here we see two types of it, where we have an energy dependence. Typically, this is then what it could look like with an ion chamber based survey meter, where you have it only in up here, up in the way up in 800 kilo electron volt, which is on the therapy side, of course. But here, 100 and down, we've got everything from 1.2, 1.15 down to 0.30 something when it comes into the mammo range. So the indicated and the actual. So here it's indicating 0.4 out of the actual. So it's underestimating the dose when we're here in the lower KeV ranges, which could be mammo and lower radiography. Only up here, which is typically around 60 something, is the true reading correct that we're reading from an ion chamber based one. To compensate for this, we need to know what is the KeV, which is the mean energy then of the spectrum. And to do that, we need to figure out, we can simulate and then look up and see, okay, we've got a CT scanner here. Typically, the total filtration is 8 millimeters. The anode angle is 7, and then we can simulate and see what is the expected mean energy of that spectrum. Then we can go in and look at how many people do that. Well, not very many. So, especially, and then if you look at mammography, then since it's so attenuated here, 0.4, 0.3, when you have the lower, you have the very low energies, and the low energies, and there's also underestimating of the reading. Then of course it's easy to say that that's so low radiation, we don't need to worry about it. Well, have you actually compensated the values that you're looking at? Have you estimated what the spectrum, the energy spectrum is, the mean energy? Have you done that? And are you doing a proper reading? Do you know how to compensate for it? Well, like we said before, with the scatter probe, we have the possibility here of, since we have the solid state, we have the diode, we have the estimation of the mean energy of the spectrum, we can automatically compensate for the energy dependence which we have in the solid state instruments, or the solid state probe diodes. That means that we have a dip like this. It is natural and it occurs but you see that dip, that knee, that change is very much smaller because we can compensate, and in that area it's very difficult to do the estimations because it's a very difficult to distinguish. But with the electronics that we have, we can estimate the mean energy, so we can automatically go in and compensate so that we are within plus minus 10% with reasonable margin as well. to the actual levels of radiation that we have in here. So there's no more 0.4 measurement compensation required. It's no compensation required because we're within plus minus 10%. So this is an explanation why, one of the explanations why there may be differences in the readings here. And we're very humble. We know that it is. We know that the reference values many times are based on ion chamber based survey meters. So it needs some discussion, needs some understanding, needs some evaluation of the situation. What was actually done before, and how does that match the values that we're producing today? All right. So what we see here, what we're talking about the energy levels here is, again, let's say that we have an exposure which is then like the actual here. It's a sharp edge, and then we've got a small spike, and then it drops. Traditional survey meter, of course, having a slow response, would take a time to rise, and then it wouldn't detect the top. It would be a small bump, and then it tapers off towards the end. So a possibility is that, yeah, well, it captures the integral of it. The accumulated dose might be correct in this, especially here at 100 kV acceleration voltage, which is 50 keV mean energy in the spectrum. But what happens if we look at 160 kV, a CT scanner, for instance? And that's the mean energy would then be about 65, 70 keV. That means that we would overestimate the reading that we have. It wouldn't pick up any small sparks or bursts in here, but maybe the dose would be the same. Looking at mammography or lower 35 kV, which is then the low rad, it would underestimate, because the mean energy is 26 keV, and you remember that the energy dependence curve is pretty slow here. And then if we're looking at 20 keV, which is a mammography with rather high kV, but still 20 keV, it would severely underestimate the dosage to it, if you don't do the manual compensation for it, which our experience is that, well, sometimes it's not taken into account. All right. So those are some of the issues there that we might have. Now, then again, some are saying that, well, when we're looking at the ambient dose equivalent and air karma, well, it's the same more or less, and we'll just use that to be on the safe side. It's linear. Unfortunately, it's not. It does have a difference, and this is if you look at the curves here that we're seeing, there is a risk of underestimating ambient dose equivalent when we're above the 40 keV, which is or 40 k and 29 keV, which is where the balance is. So here we're underestimating ambient dose equivalent, the Sievert values, if we're approximating it with the air karma. And here we're then might be overestimating it, and because then we have a conversion when we're doing the conversions of it. So there's a risk as well when we're in that area. So this is then just an attempt here to explain a little bit how it works. The scatter probe. We're of course confident that the scatter probe works fine. That we have a well-functioning tool. And I hope also that we've explained a little bit what could be the reason for discrepancies between the scatter probe and traditional ion chamber based, typically, or also other solid state instruments when it comes to doing that. Yeah, and we have a question here, Mr. Modi. Can you activate your microphone or type something into the chat. So I'm not getting any audio here. Mr. Kumar as well, and Mr. Bagchi. Would you mind? There's a chat. We have a chat, and there's also a question box there. If you could type your questions there, maybe we can do it that way, because I'm not picking up your audio. There we go. Yep. We'll be able to share the presentation that was from Mr. Priyankesh Singh. It's not an issue. We'll be sharing the presentation with you. Mr. Kumar or Yogesh Kumar, if you could, there we go. The lowest radiation levels that we can measure. That's a very good question. And then for the automatic trigger levels, when we look at the manual, I think it's 5 microgray per hour. That's the automatic trig level that we have. Now, of course, that's quite low, but there are lower that we can measure by going into the free run mode that we looked at. And that means that you have a manual trig. You'll just start the measurement and you stop the measurement. And for that, there is no threshold any longer. So that will then accumulate all the dose that you that we have. So then there's no threshold. Yeah, that's again, if it's lower than 0.6 mR per hour. If we go to the free run mode, we will be able to pick measurements up which are lower than that, because there's no trigger threshold. It will just read any measurement, any radiation that we have in there. But if you have normal mode, that's the limits that we have. Manual mode, which is free run, then we'll have no lower limit. And then from Priyankesh Singh, what would be the minimum distance for placing the scatter probe from the source? Well, there is actually no real minimum distance. There is, though, when we're looking at from a radiation point of view, typically if there is the regulation, if we start there, when we're looking at leakage, we should measure the leakage dose at 1 meter distance from the source, which is then the focal spot. So that's the measurement that we 1 meter distance. That's according to the regulation. Of course, we can measure closer, but then we need to compensate using the inverse square law. So we can be at instead of 1 meter, we could be at 0.5, half a meter. Of course, then the distance is shorter by half. That means inverse square law, half. So then we need to multiply the radiation, or the radiation is going to be 4 times higher when we're half as close. So that's how we need to work that out. But that's with the inverse square law. From a measurement point of view, Of course, it's good to be a distance away, because if it's a crack, if it's a hole, when there's a leakage or anything like that, the radiation spreads like a sphere through a pinhole. And if we're very close, we may not we'll detect the radiation, but the radiation may be only in part of the detector. And to get a solid reading, we need to fully irradiate the detector. So it's better than to be a little bit distance away to pick that, to measure, if you want to measure the actual dosage. To find this a hotspot, that's better. That's easier. You just need to move it around during the exposure slowly, but that's it. So those are the factors. If you want the actual value, then move away a little bit. If you just want to detect hotspots, then you can be closer to it. All right, what do we have here? Because, Mr. Vikas, we have the trigger level here is that the question here is then if the trigger level, if we have normal trig, which is 0.6 mR per hour, does that mean that we will not be able to detect radiation which is less than 0.6 mR per hour? Well, that's the definition of a trigger level, I would say. So then we might be, then we'll be, we won't be able to see that, because that's of course the definition of a trigger level, that it needs to go beyond that to before we can actually see something, before the measurement starts. So that it needs to be beyond the trigger level in normal mode to trigger the measurement. If the radiation is lower than that, well, then we need to go to free run mode. We need to start the measurement, make the exposure, stop, and capture the data. Then we'll be able to measure, get a good measurement reading. Then we pick everything up from 0 up. Mr. Yogesh Kumar, question is here. Sometimes scatter probe automatically measures the radiation without any exposure and continuously detects. What is the reason? Well, again, there is background radiation, and there is also a little bit of noise, and there's always something happening that it picks up for a radiation level. And it usually is then, let's see if I can find that presentation or that slide that we had. Didn't really find that one right there. So, but it does pick up things. But what we need to look at is what is the accumulated value of it? What is the dose that we're seeing? What is the air karma that it's picking up over time? And if you remember the screen I showed you previously with the peak dose rate, which showed something, there was no accumulated dose in that value, because it was so minuscule that we didn't actually see it in there. So it's very low, and it has also to do with the let's see, where do we have? I had a slide here that I'm not finding right now that illustrated that fact. You'll pick up something, but it's actually so little that it doesn't really show. Yeah, no, sorry, I can't find it here, but it's the thing is that it may show something, but it may be 0 point some nanogray, which is very little. But it is a digital instrument, so it will show you that. If you have an analog instrument, it may not show you that. If you have an analog instrument which doesn't have the same resolution, it will not. It will just round it down to 0. It'll show you nothing, and that's what we have. We did have in the first versions of the software a bit of a glitch. The filter we had in there allowed also negative dose values to be shown. And of course, that is a little bit of a, yeah, it's not very intuitive. So we modified that a little bit. So now it's now we have a bit of better filtering effect with it with the more recent software versions. There we go. There we go. Here then we had a bit of a question here. Dose with distance ratio or equation from Santa Silvacci, and I don't really understand the question, but what we're doing is we're with the air karma and with the values that we're showing is at the point of the detector. So we need to factor that in as well. So then, of course, distance changes the radiation measured, the measured radiation, of course. If we move away, we'll measure less radiation, of course. There is a way to work with that with templates in the Ocean Next software. So where you can apply the inverse square law. So you measure the distance and the assumed distance, and the software can automatically compensate for that. But that's something that you need to do more. And what best setup to measure the scatter and leakage radiation? Well, the leakage, of course, is easy. You just close the collimator, crank up to maximum or whatever the legal limits are, and then you measure the leakage. And you'll see when you place the probe there, I would recommend a tripod. With the scatter probe, the thread in it is the same as for a typical camera tripod, so you can get them really get a cheap tripod, not a problem. Because you don't want to be in the room until you know that the radiation levels are low, and you don't know that until you measure first. So you should have something on a tripod on a good position. Make your exposure, see how that works out. Look at put that into the formula for the workload. How many exposures like this is it? And then you make all the calculations. And you do that in the 5 directions at 1 meter distance from the probe, from the tube head. That's for leakage. That's what you do for leakage. For scatter, well, then there are legal limits that vary a little bit from country to country. And that's typically you place it behind the lead glass to see what's going on there, to see that the operators, the staff, are safe. So then you place the PMMA like we showed before and make a measurement right there. Then you go through the workload and the calculations, how many like this would happen in a typical hour, and there you make your estimations. It is then tempting to move around and to sniff around with the probe with manually like this, but and I've seen customers do that with the traditional survey meter with the ion chamber based that looks like an iron, and you move it around. Now you need to factor in the response time again. So what are you doing if you're moving it across and there is a hotspot somewhere, or there's a door jam, there is maybe a small crack or a small defect in the door jam that lets some radiation escape past there. If you're moving it like this during an exposure, you may not pick up that dose rate level if you're moving it around like so. So then what you would need to be doing is what I would recommend is put it on a tripod and measure it, and then move it, measure, move it, measure, move it, and measure. So you make several measurements along the way to take into account the response time and what you're doing. Moving it around like this, like a ping pong racket, may not be the best usage of it when you're using it. So it needs to be moved around slowly if you want to move it. Scatter probe, of course, is quicker, a quicker response, has a shorter response time. So then you may there's a less risk of missing something, but still you need to be very careful when you're moving it if you want to measure the leakage. If you just want to get out of there, submit a paper and then move out, well, then you can fiddle around like this, like a ping pong racket, and sign off and then do something else. But if you want to measure properly, you need to take your time to do it. There we go. Oh, Yugesh Kumar, that was answer to your question. Can we measure in the hand? Yeah, you can, of course, but you need to allow for the response time if you're holding it in your hand, right? If you hold it in your hand, fine, that's good, but move it, taking into account the response time. Typically half a second, give it time to pick up. What is the minimum limit of free run mode, and what time for set measuring time? Well, I assume that we're talking here about the measurement time for the exposure time for the modality, and that doesn't really matter, but it's for free run, any time will do. So it will start the measurement when you press the start button. It will start ticking, tick, 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 and then when you press the capture button, it will stop and accumulate the data. It used to take quite a long time in the earlier versions, but we've updated the software, so that is now quicker also. So that's so I would then, to make it realistic, it's always good to have a long exposure time, because then you can move around and maybe at least move a little bit for each exposure when you're checking the door, for instance, or some other. It is tricky to compare long exposure time, and especially when you're looking outside a lead-lined wall. The radiation should be 0, right? But if you have an instrument showing 0 and the other one showing a value, well, which one should you trust? Is there radiation, or is there no radiation? Well, I had one customer looking at that, and they found that they had 0.04 micro or MR per hour, which happens to be the drift value, the maximum drift in an ion chamber based survey meter. I don't know, but maybe that could be the case, that it was drifting. It wasn't picking up anything, it was just drifting and then arriving at 0.04 micrograde per hour. That could be the case, because the scatter probe was detecting nothing, not even in a free run mode. So that would be my guess, of course. I might be biased, but that could be an explanation that they're showing different things. We're not drifting that much, and we're picking up some peak values, but if there's no radiation, it's not picking up anything there. So that could be the case. How to overcome this issue of continuous measurements? I'm not sure what issues we're talking about there, as was from Yogesh Kumar. So we'll leave that a bit. From Patel, what is the trigger minimum measurement limit for free run mode? Well, we said again that if we're in free run, there is no trigger level. That's what we said before. There is no trigger level. It picks up everything. So it will, whatever radiation, it will then detect it. What is the ideal selection mode for area survey tests and tube leakage, 10 or 100? Well, that is for tube leakage, it is 100 square centimeters. That is the standard, what it says. And then, of course, you need to decide, do you want to follow the standard and be compliant, or do you want to do something else? That's up to you to decide. But the standard, the global standards call for 100 square centimeters. So you need to decide. There is another one with a 10 square centimeter, and that is for barrier testing in some certain areas that you need to look at. But those are described in the standard. So you need to decide, do you want to follow the standard or not? If you do, then 100 square centimeters is what is called for. Because when we tried free run, there was background radiation. After pressing reset, it was not getting 0. How to reset? Don't really understand the question here. There was background radiation. There's always background radiation, but the reset button that we're using, and which is, by the way, this button up here that I'm now circling on the screen, that's the reset button. If we press that, it will reset the scatter probe to background radiation. Similar thing as you do with an ion chamber based. You press and you set it to 0 to background radiation, but that always varies a little bit, and that's what you need to do. So I don't have any other suggestion than to reset, and that sets it to 0 background radiation at the point of reset at that time. Of course, background radiation may vary depending on where you are, of course. So that impacts it, but there's not much to do. We need to have one defined 0 point, and that's when you make the reset. That's it, reset to that background radiation. And as I explained before, that we initially had some a more open filtration when it came to background radiation. So we had people registering negative dose values, which doesn't really make sense. But that is due to the fact that background radiation varies just a little bit, just very, very, very tiny. The thing is, the scatter probe is so sensitive that it will then pick up the differences in background radiation. So if the background radiation drops a little bit, well, then the reference is gone. So then it will register negative value in changes. And so we modified that a little bit. So we have a slighter a better filtration of it. So now if you update to the latest software, Ocean software, and you can do that by going to our website and then finding the support pages or the resource center, which is in the website. Or if you have My RTI, go to My RTI and find the resource center, and there you have the possibility to download the latest software, which is now version 4.4. So that might be helpful if you have trouble with the reset of it in there. And of course, changes in the background radiation, you won't really pick that up if you're doing a survey, which is for one exposure, because that will you start the measurement, make your exposure, maybe 1 second or 5 seconds in maximum, and then you capture data. That's maybe a total of 10 seconds. Then the variations there in the background radiation would not be that big. So it's when you have it running for minutes, that's when you may have an impact on the back changes in background radiation. Anyway, it's always good to have the latest software though, so please go to our website and update when you have Smita and Chan, is there an option to reset background radiation to 0? Sometimes they show even without any radiation. Yeah, there you go. And that's, I think, the peak radiation values that you're looking at. And like we said, that this is then a possibility for us. That's then the peak. So we need to differentiate between the peak values and the actual values here. So peak values could be very short events in there. So peak rate here, that's the peak. It could be something very, very, a very quick event of something like that. And that's then, we've explained that, and that's and not to worry about. And that's something that we need to, another question that we need to look at. How to overcome the continuous measurement as unconditional without exposure. This is a major issue during measurement, means it gives a false reading. Well, beg to disagree, Mr. Kumar, Yogesh Kumar. If it's a false reading, it's reading what it's picking up. So there is something in there that's giving a peak, allowing us to collect the peak rate. If it's a false reading, I don't think so. The thing is that if you have a slower system, maybe an ion chamber based, it may be so slow it doesn't pick it up. So that may be the false reading, that it's not picking these quick events up. That may be a false reading. So it depends on what you're used to and what you're expecting, and what are you looking for? Are you looking for the very, very peaks, or are you looking at the actual dose that we're capturing? Those need to be to work out. You need to decide what you're looking at, and what you're measuring and what you're trying to detect, and that we're picking up these peaks. Yeah, maybe we're picking up a peak, but it may not even register in the accumulated dose. So those are two different things on what we're looking at. So yeah, we need to focus on what do we want, what are we looking at? The peaks. If you are, then you need an instrument with really quick response times, right? If you have an instrument which is slow, then you're not looking at the peaks. Then because it cannot detect those quick events. It has a slow response time. We illustrated it before. The response time. It takes time for it to respond to it. So then the question is, if you're comparing it, you need to understand what you're comparing it to. Now, if you have an instrument that cannot detect it, it does not mean that it is not there. It just means that you cannot measure it. With the scatter probe being a quick instrument, then you can actually detect it. Well, then you've got a new world that opens up to you and seeing what actually is going on. So that's where you need to understand what's happening there. So I hope that was answered there, Yogesh Kumar. And then we've got Ms. Patel for scatter radiation with detector we use for free run mode. Either or. Doesn't really matter. It depends on what you want to measure. Typically, when you're doing a survey, a room survey, it would be more practical to use the large one, the 100 square centimeter, because you have a higher sensitivity, of course. With a larger detector, you have a higher sensitivity, even higher sensitivity than the smaller one. So that's for room survey, for instance. That I would recommend that. Yep. So that's where we are. We have another one. Yeah. Rakesh, you had another question here. I got it on my WhatsApp, but I can't really see the question you're referring or the message you're referring to. Ah, the audio quality is poor. I'm sorry about that. It's I'm getting different messages, mixed messages here. I'm getting that it's okay in many areas, but yeah. Anyway, this has been recorded, so we will be making that making it available to you as well. Oh, there we go. I have a repeat here from Mr. Kumar, Yogesh Kumar here. My question is about the condition of the idle scatter probe without any measurement. It beeps even in that idle condition, and exposure time is continuously increases, and how to stop that issue. Well, if you are in free run mode, you're starting the measurement, and the beep or the ticking indicates that the measurement is ongoing. It's not like a GM tube that is actually registering it. It's just to illustrate that something is happening, that we have a measurement going on. And so that's the only thing. And the time, if you start the measurement with free run mode, the measurement is time is starting. So it's not the exposure time that we're seeing; it's the measurement time that we're starting, and that keeps on running. So that's just and will be a help to you if you're doing it. If you're doing a long exposure and you're moving it slowly along a door jamb, and then you see where, and then when you stop, you get the waveform, and you can see after how many seconds do I actually get, like this one here. It's here after about 5.5 seconds, I get the peak. So then if I'm moving it slowly from the bottom of the door up, and then I see, okay, and here is the top of the door, I know that, okay, at the middle of the door, that's where I have a hotspot. So that's why we have it's not the exposure time, it's the measurement time that we're seeing here. That's the time base. That's the measurement time. We start the measurement here, and here we press the capture button. So that's not the exposure time. Ticking also indicates that, yeah, and the measurement is now ongoing. Tick, tick, tick. That's what we're doing. So, and that's just the way for you to understand that something is good. Something is happening. Some measurement is going on there. And that's done for the free run mode, which you're using when we're doing low radiation level measurements. That's where we are. All right. So, do we have any other questions? So, and I'll just summarize it then with the scatter probe. We've got a solid state instrument, sensitive and has a fast signal response. And that, I think, what throws you. We had some questions here about, false readings and stuff like that. Well, I beg to disagree. It's a reading because something is happening. There's the radiation event that we capture. We can capture it with a scatter probe, but apparently not with some other instruments. So that's the new way of looking at it here. Automatic energy compensation means that we get a good reading automatically. The trigger levels, we have the choice of automatic or manual trig, which is in free run. Automatic trig for typical exposures when we're looking at leakage and stuff. Room survey, we may need to go to a manual trig, which is the free run mode. Selectable values for air coma, ambient dose equivalent, which is sievert, and then mean energy if we want to do research level, stuff like that. MR or microgray, regulation size, and measurement areas is 100 square centimeters or 10 square centimeters. And then we also have the possibility of having a waveform graphic, which comes in quite handy, because we do have the possibility then of detecting, is it just noise? Where does the radiation appear? How does it look? Does it look something like something reasonable that makes sense? So those are the things that we can make out from the waveform graphic, and of course then also the calibration cycle. Now, just to illustrate again on what we're up against here, we have got a new technology, and things happen over time. So just to give other things that just as a final sign off here, that what we're up against is then things that look pretty good in 2005, but that same thing may not look so good 10 years later on. So things happen in the market, new things appear, and on that note, I'd like then to thank you for your attention, and yeah, like I said, we'll be happy to help you further. If you have any further questions after this, please contact the team at Bergen Healthcare, and they'll be able to help you. And if they need more help, we'll be happy to in the future. So thank you very much for your attention, and yeah, see you next time. Bye-bye.